Hi students, this is our course code 19MA203 Complex Variable and Differential Equations. In this course, we are going to see the Unit 5 for application of partial differential equations. So this is an introduction. In science and engineering problems, we always seek a solution of differential equation which satisfies some specified conditions known as boundary condition. The differential equation together with boundary conditions constitute a boundary value problem. In the case of ordinary differential equations, we may first find the general solution and then determine the arbitrary constant from initial values. Next, we are going to see the classification of partial differential equation. The general form of non-homogeneous second order partial differential equation is a of x comma y is a of x comma y into dou square u by dou x square plus b of x comma y into dou square u by dou x dou y plus c of x comma y into dou square u by dou y square plus small f of x comma y comma u comma dou u by dou x comma dou u by dou y equal to capital F of x comma y. So here x and y are the independent variable, u is a dependent variable. The coefficient of this second order we can take it as capital A. Then the coefficient of this one we take it as capital B. Then this is coefficient of this one we take it as capital C. So from this equation we have to check the condition. If the condition b square minus 4ac is less than 0, then it is called a elliptic. If b square minus 4ac equal to 0, then it is called a parabolic. If b square minus 4ac greater than 0, then it is called a hyperbolic. So next we are going to see the examples based on this classification. Classify the following PDE. Dou u by dou t is equal to dou square u by dou x square. So compare this equation with the general equation. So there dou square u by dou x square coefficient is capital A. So here capital A is equal to 1. Then here the dou square u by dou x dou y term missing. Therefore b is equal to 0. And another term dou square u by dou y square term is also missing. So c is also equal to 0. Now check the condition b square minus 4ac value is equal to 0. So therefore the given partial differential equation is a parabolic equation. Next, classify the partial differential equation dou square u by dou x square plus dou square u by dou y square equal to 0. So from this equation, what is the capital A? Capital A is equal to the coefficient of this term 1. Then the capital B, the coefficient of dou square u by dou x dou y. So that term is missing. So b equal to 0. Then the coefficient of dou square u by dou y square is c. That is c is equal to 1. Now check the condition b square minus 4ac is equal to get the minus 4. So the minus 4 is a less than 0. Therefore, the given partial differential equation is a elliptic type. Next problem. Classify the following partial differential equation. Dou square u by dou x square plus 3 into dou square u by dou x dou t plus dou square u by dou t square equal to 0. So here capital A is equal to 1, capital B is equal to 3, then capital C is equal to 1. Now check the condition b square minus 4ac which is equal to 9 minus 4, that is 5, greater than 0. Therefore the given partial differential equation is a hyperbolic. Next we are going to see the outline of this unit. So first session, one dimensional wave equation with zero initial condition, initial velocity. Session 2, one dimensional wave equation with non-zero initial velocity. Next session 3, one dimensional heat equation with zero boundary condition. Session 4, one dimensional heat equation with non-zero boundary condition. Session 5, two dimensional heat flow equation. So now we look into the session 1, one dimensional wave equation with zero velocity. So with zero velocity, here this is a one dimensional wave equation. The one dimensional wave equation is dou square y by dou t square equal to a square into dou square y by dou x square. Where here y is a dependent variable, then t and x are the independent variable. That is y of x comma t, and a square, this a square stands for the capital T by m. Capital T is nothing but the tension of the string. M is nothing but the mass per unit length of the string. So this A square values always must be a positive value. Next we go into the assumption. Consider an elastic string of length L which is tightly stretched and fixed at the two endpoints. Take one fixed end as the origin, capital O of 0, 0 and the other end, capital E of L, 0. The string in the equilibrium position as x-axis and y-axis through the origin and perpendicular to the x-axis. We require the differential equation governing the motion when the string is set vibrating in the vertical plane. We may have the following assumptions. The first one, the motion takes place entirely in one plane, that is the xy plane. In this vertical plane, each point of the string moves in a direction perpendicular to the equilibrium position of the string. Next, third point, tension capital T of the stretched string before fixing it at the end of its constant at all times and all the points of the deflection string. Next, fourth point, tension T in the string to be so large that the gravity may be neglected in comparison with it. Next, fifth point, the effect of the friction is negligible. Sixth point, the string is perfectly flexible. It can transmit only tension but not bending shearing forces. Next, seventh point, the slope of the deflection curve at all points and at all time is so small. Next point, M mass per unit length of the string. So these are the following 8 assumptions we are going to see in the problem. That is a consider a string of length L. That is a consider a string length L. So we have to fix the one end fixed, another end is also fixed. That initial point they take it as x equal to 0. Then the final point they take it as x is equal to L. Then if we give any vibration is there, so it takes the following assumptions. So next we go into the possible solution. So for solving the one-dimensional wave equation, we have the three possible solutions is having. So one is y of x comma t is equal to a1 e power px plus a2 e power minus px into a3 e power apt plus a4 e power minus apt. Next second one, y of x comma t is equal to a5 cos px plus a6 sin px, a7 cos apt plus a8 sin apt. Then third one, y of x comma t is equal to a9x plus a10, a11t plus a1t. So from these three possible solutions, we have to choose the second one as the most general solution, because here only we have the trigonometric terms is having. So sine means that is a vibrating a string. It have either the sine wave or cos wave. So it includes the sine and cosine. So therefore we have to consider second as a most general solution. So these two solutions we won't take. Next we look into the problem. Consider the zero velocity problem. A tightly stretched string of length L is fashioned at both ends. Motion is started by displacing the string into the form y is equal to k into Lx minus x square, from which it is released at time t is equal to 0. Find the displacement at any point on the string at a distance x from one end at time t. That is in this problem, that is we are considering a string length L. So it is fashioned at the both endpoints. So after that is we have to take x equal to 0 to x is equal to L. The motion is started from the displacing by the string into the form y is equal to this form. Then at from which it is released at time t is equal to 0. At time t is equal to 0, the string is released. Therefore, it comes under the zero velocity problem. Next solution, the displacement function y of x comma t of the string in the solution of the wave equation. So this is our wave equation. Then already we know where a square is equal to t by m, which is equal to tension by mass. Next, solving the equation 1 by method of separation of variable, we get the following three possible solution. So out of this solution, we have to select that solution which suits the physical nature of the problem and the boundary conditions. So now we are going to see the boundary condition. So this is the boundary condition. So initially the length of the string is x is equal to 0. So that value is also 0. Then initially the strength of the string x is equal to L. the displacement is equal to 0. Next, initial condition dou y by dou t of x comma t is equal to 0. That is initially rest at t is equal to 0 is given. So therefore here this is the initial velocity. So here the initial velocity is 0. Next, fourth one, y of x comma t is equal to 0. That is the motion is started, that value k into Lx minus x square. The suitable solution which satisfy the above boundary conditions is y of x comma t is equal to c1 cos px plus c2 sin px into c3 cos apt plus c4 sin apt. So now we have to apply the first condition in equation number 1. So first, what is the first condition? Y of 0 comma t is equal to 0. So we have to substitute x is equal to 0 in this equation. So we'll get here the cos 0, here the sin 0. So here no x term is having. So this one keep as it is. Then what is the cos 0 value? 1. Then c1 only will come. Then sin 0 value is 0. So c1 into c3 cos apt plus c4 sin apt. So here we have to identify which value is equal to 0. That is c1 is equal to 0. If we substitute c1 equal to 0, the solution won't affect. So therefore, we put c1 is equal to 0. If we put c3 and c4 both are same term, so therefore we can't put c3 and c4 equal to 0. So therefore the solution becomes y of x comma t is equal to c2 sin px into c3 cos pat plus c4 sin pat. Now applying the second condition in equation number 2. So in this equation only we have to apply the second condition. What is our second condition? Y of y of L comma t is equal to 0. So here we have to substitute x is equal to L. So C2 sin PL into C3 cos PAT plus C4 sin PAT. For this term, no x term is having. So here no need to replace. So now if you put C2 is equal to 0, the solution become a trivial solution. So therefore we can put C2 is equal to 0. If you put these terms equal to 0, this is also trivial solution. So only possible we can choose a sin PL is equal to 0. So keep this PL this side, then bring the sign to this side. We can write the sin inverse of 0. So sin inverse of 0 will get the n pi. So therefore L is equal to n pi by P is equal to n pi by L. So after finding the P is equal to n pi by L, so substitute in the equation number 2. So we get y of x comma t is equal to C2 sin, here replace P is equal to n pi by L. So n pi x by L into C3 cos n pi at by L into at plus C4 sin n pi at by L. Next one, before applying the third condition, that is the third condition, we have to differentiate. That is a dou y by dou t of x comma t is equal to 0 having no. So before that, we have to differentiate this third equation with respect to t. So if you differentiate with respect to t, the first term is not having a t. So keep this as it is. Then here only we have a t having. So differentiation of cos is minus sin n pi at by L into differentiation of this one is n pi a by L. So that we are written here. The next one, this term, differentiation of sin is cos n pi at by L. Then differentiation of this n pi at by L is n pi a by L. So after differentiating, so we have to apply the third condition. So what is our third condition? Dou y by dou t of x comma 0 is equal to 0. Therefore, C2 sin n pi x by L. So here if you substitute t is equal to 0, that is sin 0, see the previous step. If we substitute t is equal to 0, the sin 0 value is 0. Here the cos 0 value is 1. So we'll get the C4 n pi a by L. That is only we got C4 n pi a by L into C2 sin n pi x by L equal to 0. So from this we can calculate we already saw that C2 not equal to 0. This one already defined. So only possible is C4 is equal to 0. So this is also constant. This also should not equal to 0. So therefore from this we can find out the C4 is equal to 0. So C4 equal to 0 in substitute to equation number 3. So we get the solution y of x comma t is equal to C2 sin n pi by L into C3 n pi at by L. Then combine these two constants C2, C3 sin into cos. Then combining of these two constants we can write it as Cn, where Cn is equal to C2, C3. By substituting we get the y of x comma t is equal to this equation. So we will see in the next class the continuation of this problem.